Previously, what we learned might have been quite far from airplanes. Starting from today, we are entering content that is truly close to airplanes and closely related to our flying. Today, we are discussing the lift coefficient and two-dimensional flow fields, which are some of the characteristics. From today, we are starting to talk about airplanes, which is truly the core part of the principles of flight indeed. Every time I teach, I particularly like this diagram. This diagram clearly explains what the principles of flight are. It's about the magic related to air, and what we are learning is how to master it. This magic allows it to serve our flight. So today, let's take a closer look. We want to introduce three specific areas of knowledge today, and in order to master this magic, we need some specific methods. So we need some analytical assumptions. So how do we analyze such a problem? We need to use some special devices. And what are these devices? We'll talk about that later. First, let's discuss the principles of these devices. When we studied motion analysis in high school, we all knew that in the study of physical motion analysis, we talked about a method of relative motion, right? When observing a moving object, we can choose to place ourselves on the ground for analysis, assuming that we are standing on the ground and the ground is stationary. Divide into several moving objects. This is one method of analysis, right? Additionally, we can place ourselves on the moving object. We assume that we are stationary on this object and consider the ground to be moving. Aren't these two methods completely equivalent in terms of physics? Remember that? For airplanes, we actually use this method of relative motion for analysis as well, and this way, some experiments become particularly easy to conduct. Let's assume we are in a completely windless condition. Conducting such an analysis, we stand on the ground and observe the airplane in the sky. At this time, the relationship is that people are standing on the stationary ground. And since there is no wind, the air is still. The airplane then cuts through the sky, meaning the airplane is in motion. This is a very conventional way of movement. But this method of movement is not very convenient for our analysis. Therefore, we can also use the method of relative motion mentioned earlier by placing the reference frame on the airplane. We observe the airplane's movement from the pilot's perspective. In this case, we can consider ourselves as standing on the airplane, with the airplane being stationary, while the air moves from front to back towards the airplane, right? Then, after flowing over the airplane and generating lift, it moves to the back. We analyze this using the principles of relative motion in physics that we discussed earlier. These two methods, observing the airplane from the ground and observing the ground and air from the airplane, are completely equivalent, right? This is a very important principle of relativity that we use in the process of aerodynamic analysis. For those who just joined, you can simply click directly on your phone without needing to scan a code. So, using this principle of relativity, what kind of problems can we observe or study? In fact, we are studying the aerodynamics of airplanes. How do we use it? This brings us to our very remarkable device. It's the wind tunnel. The wind tunnel is an indispensable device for studying the aerodynamics of airplanes. So what exactly is a wind tunnel? Let's look at this typical photo of a wind tunnel. So what about the wind tunnel? Many wind tunnels are like this, a large recirculating duct, and the part inside this large chamber. We call this section the test section. In the test section, we mainly place the model of the airplane inside. Or, if it's a particularly advanced and large wind tunnel, we can even place the entire airplane inside, and then use it to conduct specific experiments. And what is the purpose of this surrounding loop? Generally speaking, there is usually a motor around this position, which drives blades to accelerate the air inside, thus creating speed. We say that during flight, we assume the air is stationary, and the aircraft is moving. Right. In this type of wind tunnel, it just so happens that the aircraft is stationary, and the air is moving, which is an equivalent effect, so we can use it for research. How does an aircraft fly in the air? With such a dynamic facility, we also want to know what the aerodynamic load on the aircraft is. So how do we measure it? At this point, a very important device is used. It's called a wind tunnel balance. We should note that this balance is quite different from the one we usually imagine with weights on both sides. This is a purely electronic balance. What it does is insert a rod, called a sting, into the aircraft. When there is a driving force acting on the aircraft, even though this force might not be very large, any small force acting on this rod will cause it to deform. By using electronic sensors to measure the deformation of the rod, we can then calculate the aerodynamic force on the aircraft. By recording this aerodynamic force and converting it according to certain corresponding relationships, we can obtain the necessary data. In fact, we can establish a relative relationship from small wind tunnels to full-scale large aircraft. This allows us to transition from designing small aircraft to designing full-scale large aircraft. This is a very important fundamental principle used in the process of aerodynamic research. Let's take a look at, the use of wind tunnels in the actual aircraft design process. This is an experiment conducted by Airbus.
The 146 is an aircraft from the 1980s. It's been around for a long time, and this winter was part of the original design and certification of that aircraft, so it's not new. This aircraft was not designed to have hybrid electric systems, but we're trying to take something that exists and turn it into a hybrid electric demonstrator. We will switch out some of the sections of the tunnel to the tunnel world to put on instead of the aircraft looks, like Aerodynamic. We're really looking at the overall design of the aircraft facility, which includes character limits, where we're trying to understand the forces on the aircraft.
I see that the yarn attached to the flying elephant is also used to observe the flow field. This yarn.
The only changes we really found or discovered during the test program were that we needed slightly bigger areas. And we needed to change the porosity of the devices in ducts to ensure that they're correctly be related to the full-scale Aerodynamic devices.
This is a wind tunnel experiment that Cooper conducted a few years ago, which was done to convert an old BAE 146 aircraft into an electric propulsion-related experiment. Let's examine how the wind tunnel is used. The wind tunnel device can determine the aerodynamics of the aircraft by blowing air, but not just any condition reveals the actual situation. The experimental conditions in the wind tunnel and the actual flight conditions need to meet certain similarity criteria. Only when these criteria are met can we apply the numbers obtained in the wind tunnel to the actual full-scale aircraft. What are these criteria? What specific similarity conditions are needed? Let's take a closer look. The first important similarity criterion, which is crucial for our flight, is that the relative angle between the aircraft and the airflow must meet a certain relative relationship. How do we express the relative angle relationship between the aircraft and the airflow? We mainly use two important parameters, one of which is called the angle of attack. For an entire aircraft, the influence usually refers to the angle between the axis along the fuselage and the relative incoming flow. We refer to this angle as the dihedral angle. And there's a second important angle called the side-slip angle. The side-slip angle refers to the angle between the relative incoming flow and the plane of symmetry of the aircraft. Once we have these two angles, we can actually describe how the airflow approaches from the perspective of the aircraft. So here, our students might wonder, does the specific attitude of the aircraft relative to the ground have any relation to the relative attitude between the aircraft and the airflow? Let's consider this question. Suppose, if the aircraft is flying like this relative to the ground, or the aircraft is flying like that, what about the relative angle between the airflow and the aircraft? Is there a relationship? Or one aircraft is flying in this direction and another is flying in that direction. This is a very important fundamental concept. It is particularly crucial for our entire semester's study. Let's think about it, whether flying forward like this or sideways like that. As long as the airflow is coming from directly ahead, then flying like this or like that. What about the angle between the aircraft and the airflow? No change, right? So, what must be emphasized here? It's that the angle of attack and the side slip angle describe the relative relationship between the airflow and the aircraft itself, not the relative relationship between the aircraft and the ground. When an aircraft is flying, regardless of its relative relationship with the ground, as long as the angle of attack and the side slip angle are consistent, it has a certain similarity. In our actual flight process, there might be such scenarios. For example, previously during an air show, the 787 aircraft, in order to demonstrate its good performance, was loaded with as little fuel as possible and did not carry passengers or cargo. At this time, the aircraft was very light, and naturally, its maneuverability was excellent. So, it accelerated directly and almost took off vertically from the runway. Additionally, we often see fighter jets climbing vertically upwards. At this point, we want to ask everyone, is its angle of attack very large? Here, we need to help everyone distinguish between these two important concepts. First, what we are talking about. We just mentioned the angle of attack, right? And then there's another very important concept called the angle of elevation. If you remember the first lesson, we talked about the angle of elevation, didn't we? What does the angle of elevation refer to? It is the angle between the aircraft's axis and the ground. And what about the angle of attack? It refers to the angle between the aircraft's axis and the incoming airflow. In fact, because their references are different, the angle of attack and the angle of elevation have completely different meanings for the aircraft. For example, here we see this is about the Cobra maneuver. Have our students heard of the Cobra maneuver? As the aircraft is flying forward, it then quickly pulls up, and when pulling up, the nose of the aircraft is already vertical. However, at this moment, the direction of the aircraft's speed does not change significantly. It continues to move forward in the original direction before descending again, and this is called the Pugachev's Cobra maneuver. For instance, during the air show a few years ago, our J-10 demonstrated this Pugachev's Cobra maneuver. So, what is this Pugachev's Cobra maneuver? During its flight process, it actually involves both a high angle of attack and a high pitch angle simultaneously, right? The large angle of attack occurs because once the aircraft is upright, there is a significant angle between it and the direction of the airflow. This angle can reach approximately 110 to 120 degrees. The pitch angle refers to the angle between the aircraft's body axis and the horizontal plane once it is upright, which is also substantial. In this situation of approximately 110 degrees, and during this maneuvering process, the angle of attack and the pitch angle are roughly the same. Referring back to what we mentioned earlier, when the aircraft is climbing numerically, when the values are increasing, what happens at this time? What about the aircraft? Its attitude angle, pitch angle, and angle of elevation are basically close to 90 degrees, right? And from the perspective of the airflow, the airflow is moving upwards, while the aircraft is moving upwards, so the airflow is directed downwards, correct? At this point, how is the angle of attack relative to the aircraft? It is in a small angle of attack state, right? That is to say, in reality, when our aircraft is flying, even if it's a fighter jet, most of the time, it is actually in a small angle of attack state. And for the aircraft we will be flying in the future, whether it's commercial aircraft or large spacefaring passenger planes, most of the time, during normal flight, they are also in a small angle of attack state. This is something we must distinguish. We must distinguish that what we are dealing with is the angle of attack. Understand? Many of the concepts we will discuss later are directly related to the angle of attack. All right, so here we have focused on explaining to everyone that an important similarity between wind tunnel experiments and our actual flight is the similarity of the angle of attack and the side slip angle. Now let's have our students look at this. Exercise. In the diagram below, OA refers to the longitudinal axis of the aircraft. OB refers to the direction of the flight path, and CO refers to the direction of the incoming flow. OD represents the horizon, top. Now, assuming we ignore the angle of the wings, which angle represents the angle of attack when the aircraft is flying? Students, please take 1 minute to answer this. Let's see if you have understood the concepts we discussed. All right, time's up. Most of us got it right, didn't we? Which option should we choose for the concept of angle of attack? Choose B, right? AOC refers to the angle between the body axis of the aircraft and the incoming flow. You must firmly remember this concept because it is crucially related to all aspects of flight safety that we will discuss later. Now that we've clarified this issue, let's look at other important similar parameters. So, what about the other similar parameters? Their impact is relatively weaker than the angle of attack, but they are also particularly useful, and I hope our students can understand them. These two parameters are called the Reynolds number and the Mach number. First, let's talk about what the Reynolds number is. In terms of numerical expression, it should be the density of the atmosphere, multiplied by the relative speed between the aircraft and the air, then multiplied by a characteristic length, and finally divided by the dynamic viscosity coefficient of the fluid. We don't need to know how to calculate this formula specifically, but we need to understand what the concept refers to. The Reynolds number reflects the ratio of the inertial force to the viscous force on an object. Salt. What does this mean? If the aircraft is flying in the air, then how does the impact caused by air viscosity compare to the inertia of the aircraft's own flight? It's relatively small, right? Therefore, at this time, the aircraft is in a state of having a relatively high Reynolds number. But if we throw this aircraft into a pool, water, as we mentioned before, is also a fluid, right? It has similar properties to air. So, at this time, how does the force exerted by the viscosity of water on the aircraft compare to the aircraft's inertia? Is the magnitude compared to before? It's more similar now, isn't it? At this point, it is in a state of low Reynolds number. The higher the Reynolds number, the stronger the inertial characteristics of the aircraft are reflected. In fact, when our aircraft is flying, it is in a state of very high Reynolds number. Let's see what different effects different Reynolds numbers have on flow length. Here, we are showing a standard Reynolds experiment. At the beginning, the Reynolds number is 355. Notice that it seems like nothing is moving, But in fact, at this time, the water is actually flowing. Also, there is a very thin line here, which will be pulled into a straight line and flow along with it. This is the phenomenon when the Reynolds number is relatively low. We then see that this line starts to shake. Then, as the speed increases further, after the shaking becomes more intense, what happens? It starts to disperse directly, right? So this is the effect brought about by the difference from small Reynolds numbers to large Reynolds numbers. When the Reynolds number is relatively small, the viscosity is relatively high. In this case, due to the effect of viscosity, the water flows layer by layer, maintaining a clear and distinct state. However, as the speed increases and the Reynolds number becomes larger, its mixing characteristics become very strong. This is the first phenomenon we can observe regarding the Reynolds number. Additionally, we can also see the effect brought about by changes in speed and Reynolds number in a smoke wind tunnel. We have seen this video before, and here we will focus again on a different aspect. We notice the shape of the area downstream of the cylinder. In fact, during the experiment, it changes richly over time. We can see that it is completely different in shape, as the separated smoke agent in the eastern area changes with speed, right? When the Reynolds number is relatively large, the separated area tends to be smaller, whereas when the Reynolds number is small, the separated area tends to be larger. Look, the two forms are completely different, right? So, in this way, actually from the streamlines, we see different shapes, and naturally, we can easily imagine that the aerodynamic forces will also be different. How much impact does the Reynolds number have on an aircraft? In fact, the Reynolds number mainly reflects its magnitude's impact on the aircraft. Specifically, for example, a flying object, when the Reynolds number is relatively small, like the mass of a butterfly in flight, and combined with its speed, it is at the level of 10 to the power of 3. For a seagull, it's larger, around 10 to the power of 5. And for our small drones, it's also approximately 10 to the power of 5. When it comes to general aviation aircraft, it reaches the level of 10 to the power of 6. When we study aircraft, we are not concerned with the exact numerical value of the Reynolds number. What we are concerned with is mainly how many zeros follow it. This is the impact reflected by the Reynolds number, which affects the shape of the flow pattern changes. Besides the Reynolds number, we have another very important parameter to describe the similarity of our flow pattern. That is the Mach number, which we have already introduced to you during the coverage process, right? What should be the definition of the Mach number? The ratio of airspeed to local speed, right? If I ask one more question, which airspeed should this be? It just work. Excuse me. It should be the ratio of vacuum complaints to local complaints, right? So, this is the significance of the Mach number. What kind of impact will changes in the Mach number have on the flow length? We can use a method called shadow graph in high-speed wind tunnels to show everyone how the flow field changes. Let's take a look. I shouldn't need sequences, right, that they ever did pretty well. The article method knows. Yes, solving for its pressure distribution in a high-speed flow field. Not a negative pressure red below. Red below the actors, Seattle. At the store become supercritical, the sharp wave that formed. The scene is green above. We can see that the colors vary according to the pressure, right? At the same time, as the flow speed changes, we can actually see that the pressure distribution of the flow field E changes. This is actually the impact brought about by changes in the Mach number. Here, the impact of the Mach number on the aerodynamics of the aircraft is mainly evident when the aircraft speed is relatively high. At this time, due to the manifestation of air compressibility, it affects the aerodynamic forces. We might have to introduce this to you later in the semester. In short, as we mentioned earlier, if we want the aerodynamic forces measured on a small model in a wind tunnel experiment to be comparable to those on a full-scale aircraft, we need to meet the corresponding similarity conditions. Our similarity conditions, first and foremost, involve two most important parameters. What are the two relative angles between the airflow and the aircraft? The dihedral angle and the side-slip angle, right? Then, there are also parameters related to reaction speed and viscosity. One is the Reynolds number, and the other is the Mach number. Once these similarity conditions are met, we can consider the aerodynamic forces generated on the aircraft. Here, let's take a look. First, I've drawn the aircraft at a very peculiar angle. Notice the direction of the incoming flow, which is from the upper diagonal to the lower diagonal. Why draw it this way? I still want to emphasize the concept of the angle of attack of the aircraft. So, what should the angle of attack be at this time? It should be aligned with the direction of the airflow, right? It's the angle between the body axis and the airflow. What kind of state is it in? It's in a small angle of attack state. It looks like the pitch angle is quite large, but the angle of attack is very small, right? Well, when the aircraft has an angle of attack and speed, it should generate aerodynamic force. At this point, we can combine all the aerodynamic forces into a single resultant aerodynamic force, which is possible, right? So this resultant aerodynamic force, it has a point of action that will act on the aircraft. At this point, we consider this aerodynamic force. When we conduct analysis, we usually don't analyze the entire system's resultant force as a whole. Instead, we typically need to decompose it, which makes the analysis simpler. At this point, we decompose it into lift and drag. So, what is lift? What is drag? Note, here I need to provide you with a definition. This definition is also a very important concept. Lift refers to the component of the resultant aerodynamic force of the aircraft that is perpendicular to the direction of the airflow. And drag, it is actually the component of the resultant aerodynamic force that is parallel to the direction of the airflow. Why is it important to emphasize this concept? We think, well, suppose the aircraft is flying like this. Well, what about its lift? It should be perpendicular to the airflow and in this direction, right? Now, if we reverse it, in which direction should we define the aircraft's lift? It should be perpendicular to the incoming flow, right? Assuming the incoming flow is horizontal. Then it is also the component perpendicular to the direction of the incoming flow, right? That's why some airplanes are able to fly upside down. In fact, this lift is actually a flat surface. It's a negative lift. And it is also perpendicular to the direction of the incoming flow, right? So this is the definition of the direction of lift. When the airplane is flying upward at an angle, the lift, is it directed towards the mountain or directly towards the vertical direction of the tree? No, right? When it is flying upward at an angle, the lift is perpendicular to the direction of the incoming flow, right? It's like this in this direction, correct? This is also a particularly important fundamental concept for us. Now, besides defining lift and drag here, we also need to consider one factor. When we usually calculate the aerodynamic force, we need it for a specific point to conduct the analysis. So, is it possible? This point might not be the point of action for the resultant aerodynamic force. For example, suppose the resultant force acts here, but the position we want to analyze is at this location. Or let's say the resultant force acts in the front, and then we need it to act at the current point. We need to analyze the effects at this specific point. Alright, when we talk about the position at this point, besides the influence of the force, what additional impact might it bring? It's an important concept we mentioned in the first lecture. There will also be an example, right? When we move the force parallelly, besides transferring the force, we must not forget there's another important aspect. It's the example. Now let's assume the airplane is flying in a symmetric state, meaning without any side slip. At this time, besides the lift and drag acting on the airplane, there is also a very important aspect, which is the example. This is the moment, and this moment will affect whether our airplane pitches up or down, regarding lift, drag, and moment if we define them according to their directions. Then, the lift that is perpendicular to the direction of the airflow and points upwards is considered positive, with lift being a positive value. Similarly, the drag in the direction opposite to the airflow is considered positive, and for the pitching moment, the direction that causes the airplane to pitch up is positive, while pitching down is negative. This is the basic analytical assumption we use when analyzing lift, drag, and moment in our aerodynamics experiments, as we mentioned earlier. Using wind tunnels, we can measure small models, the lift, drag, and moments acting on it. Furthermore, we also hope to apply the data measured on the small model to the full-sized aircraft. How do we do that? Actually, this involves a formula we discussed during the process, but perhaps it didn't leave a strong impression. However, today, we must bring this formula back, and our students must memorize it well, as it is the most fundamental concept among all. So, what is it? It is the lift, drag, and moment formulas. By using these three formulas, we can convert the parameters obtained from the small model to get, the parameters for the full-sized aircraft. Now, let's take a look at the elements that make up the lift, drag, and moment formulas. By understanding them, we can achieve memorization. First, let's look at all the formulas. There is a common component at the beginning of each formula, a large part of which is 1/2 squared. This is what we call dynamic pressure. Do you remember where we used this parameter before? Previously, in the process of Bernoulli's principle, we used this parameter, right? We have a total pressure, a static pressure, and a dynamic pressure. The dynamic pressure in Bernoulli's principle is exactly the same as the dynamic pressure here, which is 1/2 times the density times the velocity squared. Then, the second term, this S. This S refers to the reference area. What is the reference area for our aircraft? It is usually the projected area of our wings. What is the contract area? This reference area, how much is it? Then, for the following terms regarding lift and drag, there are respective lift and drag coefficients. And for the moment, about the aerodynamic center, there is a very important coefficient, which is the pitching moment coefficient. Finally, when we look at the three equations again, we can see that in the aerodynamic center formula, there is an additional term. We must highlight it separately and make sure everyone remembers it. Use this. Use a purple color to remind everyone. Why? Because many people tend to overlook it, many people tend to forget it. So, actually, from the perspective of dimensional analysis, we can also understand the importance of this coefficient and reference length in the aerodynamic center formula. Why is that? We mentioned earlier that drag is a force, while below is a moment, right? A moment should equal a force multiplied by a length. Shouldn't it? So it must be. In addition to having dynamic pressure, reference area, and coefficient, it also needs to include an additional reference length. So, this is the lift, drag, and moment formula we need to use. Now, with these three formulas, how do we connect the small aircraft model with the full-scale aircraft? As we mentioned earlier, in the wind tunnel, using a balance, we can measure the forces on the small model, right? Then we take the lift, drag, and moment on the small model and divide them by the dynamic pressure of the small aircraft model or the small model during the wind tunnel experiment. Next, we divide by the reference area of the small model. At this point, we can obtain the lift coefficient and drag coefficient of the small model. For the moment of the small model, we further divide by the reference length of the small model. This is usually a reference length on the wing. After dividing the moment by the reference length, we can obtain the moment coefficient. Here, we have obtained three coefficients, and with these three coefficients, as long as the aircraft satisfies the similarity conditions, that is, the same effects, so it's the same side slip angle, and when the Reynolds number and Mach number are similar, at this point, we can use the same coefficients and directly apply them to the full-scale aircraft. This is done by incorporating the actual flight environment's dynamic pressure when the full-scale aircraft is flying. The dynamic pressure resulting from its flight speed and altitude, combined with the reference area and reference length of the full-scale aircraft, allows us to obtain the conditions when the full-scale aircraft is flying. Its aerodynamic forces, this is the greatest use of our lift, drag, and moment formulas. Additionally, there are a few reminders I want to give everyone. First, regarding the drag mentioned here, we will learn about many types of drag later on, such as wave drag, induced drag, and so on. Here, regardless of the type of drag, we can directly express it using this drag formula. This is the first point I wanted to explain. What is the second point? The dynamic pressure. This dynamic pressure, 12RV squared, sometimes when we display it, we find it cumbersome and too long. So we sometimes use the letter Q to represent it. This is a brief explanation about these three formulas. Next, let's take a practical example to see how we use them. These three formulas. Here, I have a public experiment report for you, which is directly data released by NASA. It's about an aircraft from the past. Do our students recognize this aircraft? This is the F-14 fighter jet. The data was obtained during its wind tunnel experiments, and we can easily find this data online. All right, so here, in this report, we have a diagram like this. So let's see what information this diagram provides. First, at the bottom, M equals 2.02. Its Mach number is actually 2.02. As for its horizontal axis, perhaps the students in the back can't see it clearly below. Can those in the front see it? CL is the lift coefficient. And then, the first dynamic coordinate is at this position. Can you see it clearly? Alpha is the angle of attack measured in degrees. And then, the second. And then, the second part of the fixed coordinate is in this upper section. The letter here is negative, ion coefficient. So next, I'd like to invite everyone to join us in analyzing how this type of data obtained from wind tunnel experiments can be directly connected and used with our spring water aircraft. Let's look at the known F-14 aircraft, which typically weighs 30 tons, with a reference area of 52.8 square meters and a reference length of 3 meters. We want to calculate for you when the aircraft is flying at an altitude of 10,000 meters with a Mach number of 2.02. At this time, under the loading conditions of the wind tunnel experiment, what are the lift and moment on the aircraft when the angle of attack is 2 degrees? let's see how to calculate it. Here, I also ask everyone to open the calculator function on your calculator or phone directly, and let's take a look. First, we need to read the parameters we need from this chart. So, what kind of state did we mention earlier? We need to ensure similarity. What kind of angle similarity do we need? The angle of attack and the side slip angle should be similar, right? Here, because the aircraft is in a symmetrical state, the side slip angle is 0, so we only care about the angle of attack. Therefore, we start from a 2-degree angle of attack, then draw a line from the side to intersect with our experimental curve. Then we look down the chart to find the corresponding lift coefficient at this moment, which should be approximately 0.18. Then, after obtaining this lift coefficient, how do we get its pitching moment coefficient? We can directly move this chart upwards, and then, after aligning it with the curve, fold it to the left to get the pitching moment coefficient. At this point, the pitching moment coefficient is approximately 0.03. So this is the parameter we obtained from the wind tunnel experiment. With these two coefficients, we should then use them to calculate the parameters of a full-scale aircraft during flight. What should we do? First, we need to know the flight environment of the aircraft at that time. At this time, we are flying at an altitude of 10,000 meters. With the parameters for 10,000 meters, we can use the standard atmosphere table that we discussed earlier. By looking up the table, we can find that at 10,000 meters, the local air density is 0.414 kilograms per cubic meter, and the local speed of sound is 300 meters per second. With the speed of sound, we can then calculate the true airspeed of the aircraft, right? Knowing the speed of sound and the Mach number, we multiply 300 by 2.02, and we can determine that the true airspeed of the incoming flow at this time should be 606 meters per second. All right, now we need to calculate the lift. Do you remember the lift formula? One to rho v squared, right? Here, 1 part rho v squared corresponds to dynamic pressure. Let's first calculate the dynamic pressure. The dynamic pressure is 1 part 2 times rho, 0.41 t, times the square of the speed, 606 meters per second squared, which results in 76.18 pascals. In this process, students need to pay attention to ensuring that the dimensions are consistent. Here, we are using the international system of units, right? We are using metric units. And when calculating, if you use some parameters in metric units and others in imperial units, is that correct? No, it's not correct, right? So, we must first convert everything to the same metric units. Like here, in the metric system, we use meters for length. Then for time, it should be in seconds. And for weight, of course, the unit of mass should be kilograms. Here, we align the relevant units with 1, 2, and then V is expressed in metric units. After calculating 7618 pascals, we use 1, 2 times UV squared times the area E, and then multiply by the lift coefficient to obtain the aerodynamic force on the aircraft at this moment. It should be 722,475 newtons. What is the relationship when converting from newtons to kilograms? So the local weight. Divide by the acceleration due to gravity, right? What should the approximation be? For approximations, at this level, using 10 is already precise enough, so we should divide by 10, right? Then this corresponds to kilogram force, and then we divide it by 1,000 to get ton force. So, at this point, what do we see as its lift? 72 ton force, right? 72 ton force, right? So, at this point, we can use this parameter to check if our calculations are correct. Why? Because generally, the lift and the weight should be roughly of the same magnitude, right? So let's observe the weight of the plane. It's 30 tons, right? And its lift, 72 tons, which is roughly equivalent to 2 Gs, right? A lift state of about 2 times the gravitational force. So, this indicates that the plane having such a maneuvering flight state is basically reasonable. But if you calculate it and suddenly find that this number is 10 times or even 100 times the gravitational force, is that correct? No, it's not, right? We can easily make a judgment based on the magnitude, then from the pitch distance. And pitch moment, we should directly use dynamic pressure, multiplied by area and then by a factor. Is the reference length correct? Be careful not to omit the reference length. Finally, multiply by a pitch moment coefficient. In this way, we can obtain the actual pitch moment when the plane is flying. Now, at this time, the pitch moment corresponds to a nose-down direction pitch moment. Through the above process, we have effectively established a conversion method to derive the aerodynamic forces of a full-size aircraft from the results of small model public experiments. I hope that our students can grasp the relevant content, as this is crucial for our fundamental understanding of aircraft flight. So, where does the core concept here come from? Actually, is our lift and moment formula. Here, I would like to further explain this lift formula to everyone. First, we need to memorize this formula, which consists of components like dynamic pressure and reference area and the lift coefficient. When using this formula, if we are conducting a very strict theoretical analysis in our calculations, what density should be used in the dynamic pressure? Under very strict conditions, the density we use should be the atmospheric density of the free stream at the local flight altitude. Also, what speed is this V? As a student mentioned earlier, it is the true airspeed, right? However, sometimes we want to simplify things and analyze according to mechanical equivalence. For example, the number we get from the airspeed indicator is the indicated airspeed, right? If we correct for the errors due to position installation and compressibility, what airspeed do we get? We get the equivalent airspeed, right? So when I use the equivalent airspeed, which density should we use to calculate dynamic pressure? All right, let's take a break and think about this question.